Hi everyone. So today we're going to be learning a little bit about the atom, the structure of the atom, and how we can use the periodic table to give us some of this information. So one thing that you're going to want to make sure you have is your note sheet. You're going to be filling out your notes as we go. You also want to make sure that you have your periodic table of elements. You're going to need to look at that for a couple different things as we go through this. And you're also going to want to make sure that you answer the questions in Edpuzzle, okay? So that's how you're going to get credit for all of this. So the elements themselves, these are the simplest kinds of matter that we can have. So we've learned a little bit about all the types of matter that we have in the universe. We have mixtures, pure substances, compounds, all that stuff. And elements are pretty much the smallest we can get to. We can't break it down anymore until it just starts turning into ingredients, essentially. So if we look at the periodic table, all of these elements that exist in here all have very individual properties. For example, carbon, which is found right here, is an extremely important element to us because we are carbon-based life. Carbon-specific properties, because it's made very specifically, is how we are able to have life on Earth, essentially. So all the different elements that exist all have their own unique properties, and it has to do with what's kind of inside of those. So let's kind of delve into that. So an atom is sort of what makes up everything that exists. The atom is the smallest thing that we can break it down into. So if I want to look at the smallest piece of carbon that I could ever look at, I would be looking at one atom of carbon. If I try to break that down anymore, what's going to end up happening is we start to get those ingredients. What exactly makes up this atom, okay? So if I break an atom up, not only am I going to get a ton of energy, that's how we have atomic bombs, but it's also going to be how I get all the ingredients that make up atoms. So all the elements that are on the periodic table are all made up of the same three particles. It just depends on how many are there with what kind of atom that we get, okay? So in the parts of an atom, there's generally two regions that we look at. The one that's in the center is what is called the nucleus, okay? The nucleus is that very central location, and it's where you're going to find the neutrons as well as the protons. So both of those are found in the center, and they're sort of globbed together there, okay? In the outer part of the atom, what we have are what are called orbitals. Sometimes you'll see these called shells, sometimes you'll see them called levels. But it's essentially where we're going to find the electrons that exist within the atom. So the three main particles that we have are protons, neutrons, and electrons, okay? Now what's interesting about an atom is that this picture here is not to scale. And what that means is not only is an atom way smaller than this picture, atoms are so incredibly small that we can't see them, we can't really take very good pictures of them, even with our best millions of dollar microscopes. They're very, very hard to see because they're just so small. But if you were to look at an atom, let's say you would make the atom the size of a baseball, or the nucleus. We'll say the nucleus is the size of a baseball, so a normal traditional baseball, okay? If you were to see where the first energy level is, the first ring around it, it would be the size of an entire baseball stadium, and the nucleus, which is the baseball, would be at the center of it. So there's all this empty space that exists in the atom. So most of this stuff is all empty space. The nucleus is more like a teensy tiny dot at the center, and the electrons are way far out. So it's actually kind of funny, everything that we look at, that's matter, that's made of atoms, is almost 99% empty space. So the table you're sitting at right now, the pencil you're writing with, the paper you're writing on, that's 99% emptiness. But the fact that it's a solid and it doesn't fall right through and you don't have things falling around everywhere is because there are just so many atoms there that even though they're almost all empty, there are just tons and tons and tons of them, more than we could ever try to count. So the three subatomic particles that we have, the protons, the neutrons, and electrons, all have very unique qualities about them that make them what they are. The neutron is neutral, okay? So the big thing to remember is it's neutral, okay? Meaning it has no charge, okay? So it's not positive, it's not negative, it's just a neutron. We find this in the nucleus, and we say that it weighs a significant amount, and we're going to say that it's essentially weighs 1, okay? The proton has a positive charge, so we always indicate that with the little plus sign here, and it's found in the nucleus as well, and again, it weighs a significant amount, which we say is essentially 1, okay? But the electron is sort of this weird little guy that flies around the outside. We find them in orbitals, does not exist in the nucleus, it's found outside the nucleus, and we say that it does not weigh a significant amount. Instead, we say that it essentially weighs nothing. It is so incredibly lightweight that it really doesn't even matter how many of them are there. It doesn't impact how heavy an atom is. So when we look at an atom, let's say an atom of, I don't know, lithium. Lithium has 1, 3 protons. It has 1, 2, 3, 4 neutrons. And its electrons, it has 3 of them, but they're so incredibly lightweight that they hardly weigh anything, meaning that the weight of a lithium atom is essentially 7, okay? It's all the protons here and the neutrons here added up. That's how we figure out how much an atom weighs. So again, neutrons are neutral, they don't have any charge, protons are positive, and electrons are negative. So just real quick, we're not going to get into any kind of detail in terms of atomic models and sort of what we look at as being most accurate, but just sort of for your information, and FYI, when we look at atomic models, you're probably used to seeing this kind of like cool looking thing where you have these ellipses. I've seen this all over the place. It's always in advertisements for atoms. This is not at all accurate. It's stupid. It doesn't work at all. It makes the electrons look way bigger than they are, way too close to the nucleus. It is not a good model of the atom at all, but it's the one that's most popular in terms of what we use as humans. This is what we call a Bohr model, and this is kind of accurate. So here we represent the nucleus by its atomic symbol. In this case, it's silicon. And then we show the electrons in sort of these rings outside of it. And there's certain numbers in each of the rings for very specific reasons, which we are going to learn about a little bit later. So we say the Bohr model is kind of accurate, but what is the most accurate is what we call the quantum model. So if you've ever heard the term quantum physics before, this is where the quantum model comes from. And essentially, all these electrons that we see in an atom, we can't exactly say where exactly they're found around the nucleus. So in this case, this electron right here could be found somewhere in this region. We can't figure out exactly where, but we know it's existing somewhere in this three-dimensional region. So this is the most accurate. Again, you don't really need to know any details about that, but just be aware, like this guy over here, not accurate at all. The Bohr model is kind of accurate. The quantum model is the most accurate that we have. So orbitals are what we call, and when we look at the quantum model, an orbital is sort of that region where we're probably going to find the electrons, okay? They don't really necessarily have a place that we know exactly where they're found, but we know they're found somewhere in that region, okay? So as the electrons get further and further away from the nucleus, let's say we have a nucleus here, the first orbital is found here, the next one is here, the next one is here, the next one is here. And as we start to get further and further out from that nucleus, we can start pulling off those electrons really easily because we know that electrons are negatively charged and protons are positively charged. So the reason electrons don't just fly away into space is because they're attracted to that center, that nucleus, because the protons are positive. But just like a magnet, the further away you pull magnets, the less force you feel. The same thing happens with electrons. The further away from that center nucleus they get, the less attracted they are towards that center location. But when we look at orbitals, they're really hard to study. They're not fun. I don't particularly like looking at how everything is organized in orbitals. So when we're sort of starting out chemistry, we consider ourselves beginner chemists, we actually use this kind of somewhat accurate Bohr model because it's so much easier to see things. If you look back at that orbital picture, it's a hot mess. But if you look at this Bohr model, it's very easy to tell what the element is, how many electrons are around it, so on and so forth. So we use the Bohr model to sort of make things easier for us to understand. That doesn't necessarily mean it's accurate 100%, but it's much easier for us to study. So when we look at the electrons, okay, electrons are incredibly important towards chemistry because all the chemical reactions that we see, you think about lighting something on fire, that's a chemical reaction. The only reason that's happening is because of electrons. If electrons weren't there and they weren't doing what they're supposed to do, nothing would ever react. So chemical reactions are 100% because of electrons. And the most important of those electrons are what we call valence electrons. These are the electrons that are found on the very outside of the atom. So let's say you have an atom that has a whole bunch of shells to it, let's say 3. The valence electrons would be the ones that are on the very outside. These are the ones that I can come up and just grab and send to another atom to go somewhere else. And that's a chemical reaction. When these valence electrons move around, they trade spots, they jump to other atoms. This is how we end up having chemistry, in a sense, in chemical reactions. And the more you get away from the atom, just like if you have sort of like a classroom, the larger the classroom, the more people you can fit inside. Well, the farther out you go around the atom, the bigger those shells get, the more electrons can fit in them. So if you look at something like lead, it's number 82 on the periodic table, its symbol is Pb, it has tons and tons of valence electrons, which is why we can make lots of different compounds with it. So here's a good example. If we look at two elements on the periodic table, antimony and beryllium. Antimony is a huge element. It's really, really big. It's number 51 on the periodic table, and you can see that it has 1, 2, 3, 4, 5 shells around it, okay? That 5th shell can fit tons of electrons in it. And it's because there's so many shells that come before it. But something like beryllium, it's really small, it only has 2 shells. And that 2nd shell can't really fit all that many electrons in comparison to something like antimony, okay? So that's just sort of a comparison between the two and how as we get bigger and bigger atoms, those shells keep growing and growing and we get more and more and more of them. So, quick intro on the periodic table. This old dude here with the grody beard, that is Dmitri Mendeleev. And we're actually going to learn a little bit about how he developed the periodic table, but he essentially predicted where elements would be found once we discovered them based off the properties we have. So for example, I want you to look at the very far right side of the periodic table, where we find helium, we find neon, we find argon, and so on and so forth. These elements are known as the noble gases. And we call them the noble gases because all of the ones in that column, neon, argon, krypton, xenon, all the ones that end in on, essentially, they all have the same exact property in that they don't react with things. So Mendeleev, this cool guy here, was able to figure out that these families on the periodic table, these vertical columns, all have similar properties. They all act the same. So we're able to look at this periodic table and all of these elements that exist in our natural universe and see how everything sort of fits together in this big, giant puzzle piece. But what we really care about right now is going to be what is given to us on the periodic table in terms of information. So the first thing that we want to see is the atomic symbol, which is this guy here. So in this case, Si is the element silicon. Okay, so silicon is abbreviated by Si, and we use these abbreviations because it just makes it easier for us to fit everything on the table. So abbreviations will either be one letter in caps, or it will be 2 letters, 1 cap, and 1 lowercase, okay? So for silicon, I would never write Si for that. That's no good, okay? That would be sulfur and iodine. Okay, so if I want to represent something with silicon, I must write it as a capital S and then a lowercase I. So if you look at something like zinc, okay, zinc is number 30 on the periodic table. Zinc is Z and a lowercase n. I wouldn't write Z capital N. Ew, I don't even know what that is. Z isn't an element and N is nitrogen, so that's nonsense right there. So you want to make sure you're being very careful into what you capitalize and what you lowercase, because if you write something like Si When I ask you for silicon, I'm going to have to mark it wrong because that's sulfur and iodine. So there's very specific ways that we have to write the elements. So in addition to the atomic symbol, the other thing that's really important on the periodic table is going to be the atomic number. You're always going to find that at the very top of the table. So the one that you're looking at is in the top left corner. Sometimes you'll see it in the top right. And this atomic number is always a whole number. Okay, so let me just write that on there. So the atomic number is really important because it's the number of protons that are in that element. So lithium, the atom, has 3 protons and exactly 3 protons. It can't have any more or any less than that, or else it's no longer lithium. So if I say, hey lithium, you have these 3 protons in the center, I'm going to add a 4th one to it, guess what? Now that's beryllium, okay? So as soon as you start changing the number of protons, you're going to be changing the element's identity. The number of protons is sort of like a social security number. You have your own personal social security number that nobody else in the entire country has. It is yours. Just like that, elements have a number of protons or an atomic number. That is exactly their number and nobody else has it. So if we look at something like oxygen, oxygen's atomic number is 8. It has 8 protons. If I take one of those away for it to have 7, I don't have oxygen anymore, now I have nitrogen. So the number of protons is the exact identification of an element. In addition to that, if we have something called a neutral atom, where we have protons equaling electrons, if we remember protons are positive, electrons are negative, if we have the same exact number, let's say 3 protons and 3 electrons, that balances out to equal 0, what we call a neutral atom, okay? So if I look at something like carbon, okay, carbon, a neutral atom of it would have 6 protons and 6 electrons. That would be +6, -6, balancing out to 0. So you have to keep in mind that protons are positive and electrons are negative, and when we have a neutral atom, that means that they have the exact same number, okay? And there's a typo here. That should not say neutrons. That should say electrons. I missed that. I'm sorry. Please make sure your notes say the correct thing. That's embarrassing. Okay, so in addition to the atomic symbol and the atomic number, we're given one other really important number on the table, and that's going to be the number that's found at the bottom that has kind of the decimals with it. It's the decimally number. And that is what's called the average atomic mass, okay? And the average atomic mass is an average of all the types of element that exist. So for example, I want you to look at carbon for a second, okay? Carbon's symbol is C. It has 6 protons, so its atomic number is 6. And then its weight is 12.011, okay? And that weight, okay, that average is the average of all the carbons that exist in the entire universe. Because what's funny about elements is that they can have different versions of themselves. So we know that all the carbons in the universe have exactly 6 protons. That's necessary. But what's funny is that not all carbons have the same number of neutrons. For example, I could have a carbon that has 6 protons and 6 neutrons. I could also have a carbon that has 6 protons and 7 neutrons. Still carbon because it has 6 protons, but it can weigh different amounts. So these are what we call isotopes, okay? Isotopes are where we have different weights of the same kind of element. And we can see whether or not something is an isotope or how much it weighs by looking at its mass number, which is essentially how much the nucleus weighs, okay? And we can't have decimals for a mass number. Mass number always has to be a whole number. The reason why is because I can't have half a proton. I can't have 92.5 number of protons. That's not a real thing. I have to have whole numbers of protons in order for it to be an atom, and the same with neutrons. So your mass number is always going to be a whole number, okay? Always has to be whole. But the average, where we're looking at all those different versions, all the isotopes, that can be a decimal number, okay? And that's the one that's shown on the periodic table. Now, just in case you're not given a mass number, for example, if I say find the mass of carbon, okay? Okay, you would look at the table and you would see carbon's mass is 12.011, okay? What I'd like you to do, if you're not given a mass number, is you want to round that average to the nearest whole number, okay? Because that's going to mean that's the number of neutrons or isotopes. That's the isotope that we find the most. So the most common form of carbon is carbon-12 that has 6 protons and 6 neutrons. That's the one we're going to find almost all the time. Sometimes we find ones that are a little bit heavier, but it doesn't happen very much, okay? So if we look at oxygen, its average atomic mass is 15.999994, which means that almost all the oxygens that exist in the whole universe are oxygen-16, where they have 8 protons and 8 neutrons. So you can have atoms of the same element where they have the same number of protons, but they have a different number of neutrons. And remember, this is what we call isotopes. So if I have different neutrons, we call that an isotope. I can also change the number of electrons that are in an atom, and that's called an ion. And we're going to look at what that looks like here in a second. So here are some 3 common examples of isotopes of hydrogen. So hydrogen has a mass number of 1, and what that means is it only has 1 lonely proton that exists within it. There's no more, no less. Hydrogen 1 has 1 proton. But suddenly, if I add a neutron into the mix, now I have something called hydrogen 2, meaning its mass number is 2, because it has 1 proton and 1 neutron. Here, we just have 1 proton. And this is what we call deuterium. So it's a different version of hydrogen. It still has to be hydrogen because it has 1 proton. If I added another proton, I wouldn't have hydrogen anymore. I'd have helium. And the same thing goes for if I add an additional neutron to it, then we have something called tritium, which has a mass number of 3. And again, we have 1 proton, and now we have 2 neutrons. So I can change the number of neutrons as much as I want, makes things unstable, but I can do it pretty much limitlessly. Okay, that's how we make things radioactive. But I can never, ever, 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 ever change the number of protons if I still want this to be hydrogen. It always is 1. And here's another example of some isotopes, just so you see a different version of it. Here we have the 3 major isotopes of carbon, carbon-12 having a mass of 12, carbon-13 having a mass of 13, and carbon-14 having a mass of 14. You'll see that they all have the same number of protons because guess what? All carbons have to have 6 protons. But what changes is their number of neutrons that they have. The more neutrons, the heavier the mass gets. You can also see carbon-12 is the most common. It's almost 99% found, and that is why carbon's average atomic mass is 12.011. It's almost exactly that isotope, where we have it a little bit heavier from these guys, but only about 1% of the time. So in addition to that, we also look at what are called ions. And ions are where protons do not equal electrons, okay? So in this case here, this is a neutral atom, okay? Because protons are equal to electrons. Excuse me. So because protons are positive, electrons are negative, if we have +6 and -6, that balances out to 0. But in the case of this element here, okay, we have 5 protons, so +5, and 6 electrons, okay, which is -6. That balances out to -1. This is why we call it a negatively charged atom, where we have more electrons than protons. And then we can also look at this far side example where we have 6 protons, which is +6, and 5 electrons, which is -5, to give us an overall charge of +1, meaning it's positively charged. So you can always figure out what the charge of something is. If these things do not have the exact same number, if we have 5 and 6 or whatever it is, you can figure out what the charge would be by doing simple addition, okay? So protons are positive, electrons are negative. Again, another example. Here's a fluorine atom where we have 9 protons, 9 electrons, so we have +9, -9 to balance out to 0. On the other side, where it's an ion, we have +9 and -10 electrons. That balances out to a -1 charge. So this fluorine ion, we would say, has a charge of -1, okay? So if we know that we have changed the number of electrons, if we've lost any electrons, we call that a cation. If we've gained any electrons, we call that an anion. Again, kind of funky stuff. You don't really need to worry about that. You just pretty much need to know how to get the charge. But with isotopes, this is where we're going to be seeing the mass number provided. So U-235, that tells you that it's uranium with a mass of 235, okay? So whenever we're seeing something like carbon-14, that 14 tells you how much it weighs. So now we're going to do some practice. So I'm going to do a couple examples with you, kind of show you how this all works. I want you to make sure you have your periodic table in front of you so that way you understand how to do everything. So what we're going to see is we have elements over on the far side, symbols, and the atomic number comes next. Remember, this is the number of protons, okay? So we can see if I have to put that in that slot there, cool. And the atomic mass, we'll get to all that. So here in this first example, we have oxygen. Its symbol is O. And if we look up at the periodic table, oxygen has an atomic number of 8. So then that tells me that the number of protons must also be 8. And in this here, it doesn't tell me that I have an isotope. For example, if I look down here at carbon, it says carbon-14, telling me that this has an isotope probably because its mass is 14. So in the case of this, where it's just the regular old name of the atom, regular old oxygen, I'm going to assume that this is oxygen neutral, a neutrally charged oxygen, meaning protons and electrons are the same if it's neutral, okay? That doesn't always happen. So again, if you're not sure, just ask me and I would be happy to help you. We're going to practice this a ton. So again, if you look on the periodic table, we're not given the atomic mass, so we want to round the average atomic mass to the nearest whole number. So if you look, you see oxygen is 15.99999. We're going to round that to 16. And to find the number of neutrons, we're going to take the atomic mass. Let me write this on here, and I would suggest you write this on yours, and you're going to subtract the number of protons. So if we look at the atomic mass, it's 16. Minus 8 is 8. So that's how you're going to go through and fill out this chart. You're given different types of information for certain things, so just make sure that you use it. If you want to work with a partner for this, you can. If you have no clue what's going on, come back and see me, and I will definitely help you with this. This takes some time to get used to, so don't feel upset if you can't get this right away. We practice this a lot because it's really important for us to know what subatomic particles are there so we know how an atom is going to react chemically.